Welcome back. In this video, we're going to wrap up our presentations on lexical analysis with a discussion of how we implement finite automata using a variety of different techniques. Just a review, here's our little flowchart of how lexical analyzers are constructed. And today we're going to be focusing on this last step, the implementation of DFAs. And actually, I should say that this chart is not quite completely accurate because sometimes we don't go all the way to DFAs. We stop with NFAs and we implement them directly. And so we'll also talk a little bit about that. What if we didn't want to build a DFA and instead wanted to base our lexical analyzers directly on an NFA? So beginning now with DFAs, it's very simple to implement a deterministic finite automaton as an array. This two-dimensional array, and one of the dimensions will be the state. So we might have states here, and the other dimension will be the input symbols. And so I might have a state I and an input A, and I simply look up in that position, and there will be the next state, K, to which we're going to move. So the table stores at every particular input symbol and state the next state that the machine will move to. So let's do an example of converting a deterministic automaton into a table-driven implementation. So here is the automaton that we built last time, and recall that several videos ago we started with a regular expression which we converted to a non-deterministic finite automaton, and then we converted it to a deterministic automaton just in the last video. And here it is again. And now let's talk about how to realize it as a table. So we draw a two-dimensional table, and there are three states, so we'll need 3 rows. And I'll just label these rows S, T, and U. And then there are 2 inputs, 0 and 1. And now let's fill in the entries in the table. So in state S, on input 0, where do we go? We go to state T. So the entry in the S0 entry will be T. And similarly, from state S on input 1, will wind up in state U. So so the S1 entry will be U. Okay, and then similarly for the other rows of the table, let's do the T row next. On 1 we go to U, and on 0 we stay in T. So this row is also TU. And finally for U, what happens? Well, on 0 we go to T, and on 1 we stay in U. So this row is also TU. And there's our table. That describes the transition relation of the automaton. And now if we were to think about how we would use this transition relation in a program, you can easily imagine. We would start out, say, with our input index pointing to the beginning of the input, and let's call that 0. And we'd have to have a current state, and we start in the start state. And let's just say that that's row 0. So in this case, that would be row S. And then while, what do we want to do? We want to walk over the input and check whether and check on the and make the transitions for each element of the input one at a time. And we want to stop when the input is empty. So while there still is input, let's say we have an array of characters that is our input, and while the entry in that array is not null, let's do the following. We're going to update the state at each step, and what are we going to update it to? Let's give this array a name. Let's call this array A. So we're going to look up in our transition relation A, and what are we going to use? Well, we're going to look up the current state, and we're going to look up the input. And in that entry, using the current state and the current input, we're going to transition to a new state. And we also want to increment the input pointer. So we'll do that at the same time. And there is our loop that processes an input according to the transition table A. And as you can see, this is a very compact, very efficient process, just a little bit of index arithmetic and two table lookups, one for the input and one for the state transition table per character of input. So it's really hard to imagine having a process that's much faster or more compact than this. Now, that was one strategy for implementing a deterministic finite automaton. And you may have noticed that one disadvantage of that particular approach was that there were a lot of duplicate rows in the table. In fact, all the rows of the table were exactly the same. And we could save some space by using a slightly different representation. So instead of having a two-dimensional table, we could just have a one-dimensional table. And this table, again, would be one entry for each state, so S, T, and U. And what this table would contain is a pointer to a vector of moves for that particular state. So there'd be a pointer here, and it would point to another table, another one-dimensional table, that would say what we should do on 0 and what we should do on 1. So in the case of S, we wanted to move to state T if it was a 0 and to state U if it was a 1. And now, when we go to fill in the entry for T, we see we don't need to duplicate this row. We can actually just share this row, and similarly for U. And so this table, this representation, is actually much more compact. We just share the rows that are duplicated in the automaton. And it turns out that in the kinds of automata that we look at for lexical analysis, it's very, very common to have duplicated rows. And so this can actually result in significant compaction of the table, particularly when you consider the number of possible states. Remember, there could be 2 to the n minus 1 states in a DFA for an NFA with n states. And while the blowup is often not the worst case, it can be very substantial. And so the two-dimensional table we had in the previous slide could actually be quite large, and we can sometimes have a much more compact representation by little tricks like this. Now, the disadvantage of this particular representation is this extra indirection right here. I mean, these pointers actually take time to dereference, and so now our inner loop will be a little bit slower. We have to do a table lookup, dereference a pointer, do another table lookup, and then we can make the move. Finally, it's also possible that we might not want to convert to a DFA at all. It might be that the particular specification we gave is very expensive to turn into a DFA, that the tables just become truly huge, and we might be better off just using the NFA directly. And so one can imagine an implementation of an NFA as well. We could also implement that via a table. In this case, we would have to have a row for each state in the NFA. And we won't do them all here. But we could have rows for every state of the NFA, and then where we're going to go if the input is 0 or if the input is 1. And so in this case, and I almost forgot, we would also need a transition in the most naive or the most straightforward implementation of an NFA where we would go if on epsilon. And now, remember, because these are NFAs, in general, this will be a set of states because we might have more than one epsilon transition or more than one transition on 0 and 1. And so in this case, on epsilon, A can go to B. So this would be the set of states B. And B can go to C or D, and C can only go to E on 1, all right, and D can go to F on an input of 0, and so on. We fill in the rest of the table, and this table is guaranteed to be relatively small because the number of states is limited by the number of states in the NFA. And the size of the input alphabet. And once again, we could do sharing of common rows and other tricks like that to compress the table if we like. But now the inner loop for simulating this automaton is going to be much more expensive because we have to deal with sets of states rather than single states. So at every point in time, we're going to be tracking a set of states, and when we go to do a move, we have to look up for every state in the set where it can potentially go, including things like the epsilon moves and carrying out all possible epsilon moves, so we always have an accurate assessment of the complete set of states that the NFA could reach. So while this saves a lot of space in terms of the tables, in terms of the size of the tables, it can be much slower to execute than a deterministic automaton. To summarize, a key idea in the implementation of lexical specifications is the conversion of non-deterministic finite automata to deterministic finite automata. This is what takes a general high-level specification using regular expressions and converts it down to something that's completely deterministic and only uses a few operations per input character. Now, in practice, tools provide trade-offs between speed and space. So DFAs are faster and less compact, so the tables can be very large, and at times that's a practical problem. And NFAs are slower to implement, but more concise. And the tools give you generally a series of options, often in the form of configuration files or command line switches that allow you to choose whether you want to be closer to a full DFA, something that's faster and perhaps bigger, or to a pure NFA, something that's slower but consumes less space.